Metallurgy of Steel for Bladesmiths and Others Who Heat Treat and Forge Steel. By John D. Verhoeven, Emeritus Professor, Iowa State University, March 2005. Preface. For the past 15 years or so I have been working with practicing bladesmiths on problems related to forging and heat treating steel blades. It has become apparent to me in that time that there is a need for a book that explains the metallurgy of steel for people who heat treat and forge steels and have had no formal metallurgical education. This book is an effort to provide such a treatment. I have discovered that bladesmiths are generally very quick to catch on to the ideas of metallurgy, and consequently an attempt was made to set the level of detail presented here for the needs of those wanting a fairly complete understanding of the subject. Most chapters in the book contain a summary at the end. These summaries provide a short review of the contents of each chapter. It may be useful to read these summaries before and perhaps after reading the chapter contents. The Materials Information Society, ASM International, has published a book that contains a wealth of information on available steels and is extremely useful to those who work and heat treat steel. Heat Treater's Guide, Practices and Procedures for Irons and Steels, 2nd edition, 1995, Materials Park, Ohio, 44073. A major goal of this book is to provide the necessary background which will permit a practicing metal worker to understand how to use the information in the ASM book, as well as other handbooks published by ASM International. I would like to acknowledge the help of two bladesmiths who have contributed to this book in several ways, Alfred Pendray and Howard Clark. Both men have helped me understand the level of work being done by U.S. bladesmiths, and they have also contributed to some of the experiments utilized in this book. They are also responsible for the production of this book because of their encouragement to write it. In addition, I would like to acknowledge many useful discussions with William Dawkes and my colleague, Professor Brian Gleason, who made many useful suggestions on the stainless steel chapter. I am particularly indebted to Iowa State University and their Materials Science and Engineering Department for providing me with the opportunity to teach metallurgical engineering students about steel for over 2 decades, as well as to the Ames Laboratory, DOE, that supported most of my research activity. Many of the pictures and methods of presentation in this book result from my experience teaching students and doing research at Iowa State University. My professional career has been supported by publicly funded institutions. Therefore, I grant any user copyright permission to download and print a copy of this book for personal use, or any teacher to do the same for their students. I do not grant rights to the text for commercial uses. The copyrights to all figures with citations belong to the original publishers. Copyright permissions were obtained for inclusion of these figures. Chapter 1, Pure Iron. Summary of the major ideas of this chapter. 1. A piece of iron consists of millions of small crystals all packed together. 2. Each crystal is called a grain. A typical grain diameter is 30 to 50 microns. 25 micron equals 25 micrometers equals 0.001 inch equals 1 mil. 3. The boundaries between the crystals are called grain boundaries. 4. Below 1167 OF, 912 OC, iron is called either ferrite or alpha iron. The iron atoms in ferrite are arranged on a body center cubic, BCC, geometry. It is common to call the arrangement of atoms a body-centered cubic, BCC, lattice. 5. Above 1167 OF, 912 OC, iron is called either austenite or gamma iron. The iron atoms in austenite are arranged on a face-center cubic, FCC, lattice. 6. Heating ferrite to 1167 degrees Fahrenheit, 912 OC, causes tiny grains of austenite to form on the ferrite grain boundaries. Continued heating causes these new gamma grains to grow, converting all the old alpha grains into a new set of smaller gamma grains. On cooling below 1167 OF, 912 OC, the same type of change occurs, but in reverse order, where alpha grains replace gamma grains. Chapter 1, Pure Iron. Most steels are over 95% iron, so a good starting point to understanding steel is to study the nature of solid iron. Consider the following experiment. A 1-inch diameter bar of pure iron is sectioned to form a thin disc in the shape of a quarter. A face of the disc is now polished on polishing wheels, starting first with a coarse grit polish and proceeding in steps with ever finer grits until one ends up with the face having the appearance of a shiny mirror. The shiny disc is now immersed for around 20 to 30 seconds in a mixture of 2 to 5% nitric acid, HNO3, in methyl alcohol, called nitl, nit for the acid and al for the alcohol, a process known as etching. The etch causes the shiny surface to become a dull color. If the sample is now viewed in an optical microscope at a magnification of 100x, It is found to have the appearance shown on the right of Fig. 1. The individual regions such as those numbered 1 to 5 are called iron grains, and the boundaries between them, such as that between grains 4 and 5 highlighted with an arrow, are called grain boundaries. The average size of the grains is quite small. At the 100x magnification of this picture, a length of 200 microns is shown by the arrow so labeled. The average grain diameter for this sample has been measured to be 125 microns, where 1 micron equals 0.001 millimeters. Although a small number, this grain size is much larger than most commercial irons. It is common to use the term micro-m for micron, and 25 micrometers equals 0.001 inches equals 1 mil. The thickness of aluminum foil and the diameter of a hair both run around 50 micrometers. The basic building blocks of solids like salt and isomolecules, which are units made up of 2 or more atoms. For example, sodium plus chlorine in table salt, sodium chloride, and hydrogen plus oxygen in ice, H2O. In metals, however, the basic building blocks are the individual atoms of the metal, i.e., iron, Fe, atoms in a bar of iron, or copper, Cu, atoms in copper wire. Each one of the grains in Fig. 1.1 is what we call a crystal. In a crystal made up of atoms, all of the atoms are uniformly arranged on layers. As shown in Fig. 1.2, if you draw lines connecting the centers of the atoms, you generate a three-dimensional array of little cubes stacked together to fill space. In iron at room temperature, the cubes have an atom at each of the 8 corners and one atom right in the middle of the cube. This crystal structure is called a BCC, body-centered cubic, structure, and the geometric arrangement of atoms is often called a BCC lattice. Notice that the crystal lattice can be envisioned as 3 sets of intersecting planes of atoms, with each plane set parallel to one face of the cube. Iron with a BCC structure is called ferrite. Another name for ferrite is alpha iron, or alpha iron, where alpha is the symbol for the Greek letter A. The nature of a grain boundary is illustrated at the bottom center of Fig. 1.2. The boundary is a planar interface, generally curved, along which 2 grains of different orientation intersect. The A-planes in grain 4 make a much steeper angle with the horizontal than do the A-planes of grain 3. If grain 4 were rotated clockwise to cause its A-planes to line up with the A-planes of grain 3, then the grain boundary would go away and the 2 grains would become one larger grain. An interesting question is, why do these grain boundaries show up on the etched surface? When a metal is etched in an acid, atoms are chemically removed from the surface. It turns out that the rate of removal of iron atoms by nickel depends on the orientation of the crystal that is facing the acid. Because each grain presents a different orientation, each grain etches down at a different rate. For example, the planes that form the faces of the body-centered cubes etch far slower than other crystal planes. Hence, after a period of etching, small steps develop at the grain boundaries. For example, at the boundary of a fast etching grain, one would see a step up to the surrounding grains. The step generally causes light to be scattered away from your eye, and you see the boundaries as dark lines. If iron is heated to 912 OC, 1674 OF, a somewhat magical effect occurs. The crystal structure changes spontaneously from body-centered cubic to a new structure called face-centered cubic, FCC. This structure is shown in Fig. 1.3, where it is seen that, as the name suggests, the atoms lie on the corners of a cube as well as one atom at each of the 6 faces of the cube. Like the low-temperature BCC structure, this structure has 2 names, either austenite or gamma iron, where gamma is the symbol for the Greek form of the letter C. Historical note: the first 3 letters of the Greek alphabet are alpha, beta, gamma, alpha, beta, gamma, but there is no structure of iron called beta iron. When the structure of iron was being discovered in the late 19th century, the magnetic transition in iron, which occurs at 770 OC, 1418 OF, caused scientists to theorize a structure of iron they called beta iron, which was later shown not to exist. When the ferritic iron is heated to 912 OC, 1674 OF, the old set of ferrite grains changes, transforms, into a new set of austenite grains. Imagine that the ferrite grain structure shown in Fig. 1.2 has just reached the transformation temperature. What one would see is, first, the formation of a new set of very small austenite grains forming on the old ferrite grain boundaries, and second, the growth of these grains until all the old ferrite grains were gone. 2 important effects occur when ferrite changes to austenite. 1. Just like it takes heat energy to transform ice to water, it takes heat energy to change the ferrite grains into austenite grains. Therefore, on heating, the iron temperature will remain close to 912 oC, 1674 OF, until all the ferrite grains are transformed. 2. The ferrite to austenite, alpha to gamma, transformation is accompanied by a volume change. The density of austenite is 2% higher than ferrite, which means that the volume per atom of iron is less in austenite. Temperature reaches 1418 OF, 770 OC, the hot sample will begin to become pulled toward the magnet. As the diagram of Fig. 1.4 shows, BCC iron, alpha iron, is only magnetic below 1418 OF, 770 OC, and FCC iron, gamma iron, is never magnetic. EXP. 2. Obtain a piece of black, non-galvanized, iron picture wire and string it horizontally between two electrical posts spaced 3 feet apart. Hang a weight from the center of the wire and pass an electrical current through the wire heating it above 1674 OF, 912 OC, which will be past a red color to an orange-yellow color. Note: you will need to increase the voltage slowly using a high current capacity variable power source, such as a variac. As you heat the wire it expands and the weight drops. Now turn off the power and watch the wire cool in a darkened room. You will see the above two effects that occur at the 1674 OF, 912 OC, transformation temperature. 1. As the wire cools the accompanying volume contraction will raise the center weight, but this rising will be temporarily reversed when the wire expands as the less dense ferrite forms. 2. Heat liberated by the transformation will cause a visible pulse of color temperature increase to be seen in a darkened room. Both of these effects can be observed in reverse order on heating, but they are less dramatic due to the difficulty of heating rapidly. You can understand why heat is given off when austenite changes to ferrite on cooling by thinking about the water-ice transformation. It is clear that one needs to cool water to make it transform to ice, freeze. This means heat is removed from the liquid at the freezing temperature. The same effect occurs when metals freeze, heat is removed from the metal. So when a hot metal cools to its freezing point we find that heat is given off from the freezing liquid. The transformation from liquid to solid is a phase transformation between the liquid phase and the solid phase. Phase transformations that occur on cooling liberate heat. When austenite transforms to ferrite on cooling we have a solid-solid, rather than a solid-liquid, phase transformation and heat is liberated. On heating the reverse occurs, heat is absorbed when ferrite goes to austenite. References 1.1 Metals Handbook, Volume 7, 8th edition, ASM, 1972. Summary of the major ideas of this chapter. 1. A piece of iron consists of millions of small crystals all packed together. 2. Each crystal is called a grain. A typical grain diameter is 30 to 50 microns. 25 micron equals 25 micrometers equals 0.001 inch equals 1 mil. 3. The boundaries between the crystals are called grain boundaries. 4. Below 1167 OF, 912 OC, iron is called either ferrite or alpha iron. The iron atoms in ferrite are arranged on a body-center cubic, BCC, geometry. It is common to call the arrangement of atoms a body-centered cubic, BCC, lattice. 5. Above 1167 OF, 912 OC, iron is called either austenite or gamma iron. The iron atoms in austenite are arranged on a face-center cubic, FCC, lattice. 6. Heating ferrite to 1167 degrees Fahrenheit, 912 OC, causes tiny grains of austenite to form on the ferrite grain boundaries. Continued heating causes these new gamma grains to grow, converting all the old alpha grains into a new set of smaller gamma grains. On cooling below 1167 OF, 912 OC, the same type of change occurs, but in reverse order, where alpha grains replace gamma grains. Chapter 2. Solutions and phase diagrams. In order to understand how the strength of steels is controlled, it is extremely useful to have an elementary understanding of two topics, solutions and phase diagrams. Solutions. The idea of a solution can be explained by the following simple example. Take a glass of water and put a teaspoonful of either sugar or salt into it. Initially you will be able to see most of the solid white sugar or salt floating on the water or sinking to the bottom of the glass. However, after stirring with the spoon adequately you will see that all of the sugar or salt disappears and you only see the clear water that you started with. We say that the sugar or salt has dissolved into the water and the final liquid is said to be a solution of sugar or salt in water. What has happened to the sugar or salt? consider the salt because its molecule, sodium chloride, for table salt or calcium chloride, for the salt used on icy roads, is more simple than sugar. When the salt goes into solution, the individual molecules break apart into their component atoms, and these atoms in turn are pulled into the liquid water and are trapped in the water as charged atoms, called ions, between the water molecules, H2O, that make up the liquid we call water. For table salt, the sodium chloride molecules decompose following the reaction. Sodium chloride Na++ Cl, where the symbol Na+ refers to a positively charged sodium atom, called an ion, and the symbol Cl refers to a negatively charged chlorine atom. You no longer see the solid salt because the chemical bonds that held the atoms together in the solid have been relaxed, causing the former solid structure to disappear as its component atoms became incorporated into the liquid water between the water molecules. In general, when a solution is formed by dissolving something into a liquid, the freezing temperature of the liquid will decrease. This, of course, is why we add calcium chloride, salt to our streets and sidewalks during the winter months. The salt dissolves into the rainwater and drops its freezing temperature so that ice will not form until the temperature has been lowered below the pure water freezing temperature of 32 OF, 0 OC. This effect can be represented graphically as shown in Fig. 2.1. Here, temperature is plotted on the vertical axis and the amount of salt dissolved into the water on the horizontal axis. The amount of salt dissolved in the water is given here as a weight % of the total liquid solution. Two terms are often used to describe the amount of stuff that has been dissolved, A10Wt. % sodium chloride value can be called the concentration of salt in the solution, or the composition of the solution. Notice on Fig. 2.1 that after a certain maximum amount of the salt has dissolved in the solution, the freezing temperature suddenly begins to rise quite rapidly. This maximum composition is called the eutectic composition, and it will be discussed more later. The curves show why it is preferable to use calcium chloride over sodium chloride to prevent ice formation on your sidewalks. Phase diagrams. The geometric arrangement of the molecules in water, called the molecular structure, is the same, on average, from point to point in the water. The water is called a liquid phase. Similarly, the molecular structure in ice is the same from point to point in the ice, and the ice is called a solid phase. However, the molecular structures of ice and water are very different from each other, one being a liquid and the other a solid. Therefore, liquid water and ice are two different phases.